The screen setup is technically directly to the right. So when you go to the right, you'll go onto that screen. You got to scroll left to get to the screen.
Okay.
We can change the configuration later.
Okay. Any writing that's on right. So we have to follow twice. So this is about circuit components. We'll do semiconductor material diodes and transistors, and then get well, we just go up to digital ICs today. Do toroids and the analog stuff next week. So semiconductor materials are normally either germanium or silicon. Majority of things are silicon, except for the really high speed stuff, which uses gallium arsenide and gallium nitride. But in most cases, it's all silicon based. We have diodes and transistors. There's essentially two types of transistors made from NPN material or PNP material. We'll talk about that in a little bit. And that mostly is the bipolar junction transistors, which is the older ones. Then came field effect transistors, which operate more like a vacuum tube. So it's a voltage device to control the current between the drain and the source, where a bipolar transistor uses current on the base to control emitter to collector current. So field effect transistors have a high input resistance, where bipolar junction transistors have a lower input impedance. We have things called enhancement mode and depletion mode. We'll talk about a little bit, if I can remember which. There's also metallic oxide semiconductors in the field effect, where instead of a junction, it uses a electrostatic field to control the current flow. In the integrated circuits, the original stuff was like diode transistor, resistor transistor logic, and mostly for the last 50 years, transistor logic. And then came about complementary metallic oxide, which operates at much lower power. So that one is becoming, I guess today, and I've kind of been out of that world for a while, probably more CMOS than there is TTL today, except for the very high frequency stuff. And we'll talk about N channel and P channel. So most devices are made from silicon. As I mentioned, there's also germanium, gallium arsenide, gallium nitride. Silicon is classed as a semi-metal or transmetal on the periodic chart. So it's not a conductor, and it's not an insulator. It kind of looks metallic. It's a crystal with a very silver-looking sheen to it. They discovered that if they add impurities called doping to the silicon, they can make it a controllable conductor. Dope it one way, you can make it have positive ions or holes. If you dope it the other way, you can have it in the crystalline structure have excess free electrons. So that would be an N-type material, where P-type material would have excess holes, or basically atoms that have a missing electron. So there's it acts as a receptor, where the N-type material is a donor, has supplying electron. There's the periodic table, and you can see silicon up here is one of these blue ones, which they call semimetals. Also in there is gallium, boron, arsenic, potassium. Not sure what Sb is.
Antimony.
Antimony. Okay. The boron and arsenic, phosphorus, antimony tend to be things that they use to dope the crystals with to get this effect. We also notice here copper is one of the normal metals, and we got zinc, silver, gold. That's classed as a regular metal. Interesting, hydrogen is also one of these non-metal. So for semiconductor materials, if it's classed as a conductor, what that means is the outer shell or energy level of the atom has usually a small number of electrons in that valence, what they call the valence shell. And the energy level in that shell is essentially equal to the energy level called the conduction band. And there's this thing which isn't on this chart called the Fermi level, which this guy Fermi came up with. And at that energy level, you have a 50-50 chance of the electron being above or below. You either go, in this case, to stay in the valence band or fall into the conduction band, and that's when it's a free electron and can move over to fill in holes on other atoms around. When we have a semiconductor, there's a band gap. When the conduction band of energy and the valence band are separated by approximately an electron volt. And that's why in the semiconductor material, we'll talk about in a little bit, you see a bias voltage required for a diode to conduct through a p-n junction. That's where that comes from, is that band gap. When we have an insulator, we have a very wide band gap. So it takes a lot more energy to free that electron into the conduction band if it's an insulator type material. And insulators typically have almost a full outer valence shell, which, and I don't understand the physics, but that makes it harder to energize an electron and free it for some reason. Okay, so we look at a copper atom. I think that's copper. 14, yeah. And then we've got 4 atoms in the valence shell. So they're at an energy level normally that's very close to the conduction band of energy. So it doesn't take a lot of energy to move that electron out of there and make it what we call a free electron. If we look at the no, that's done. Copper does 4. This normal silicon crystal, we have what they call covalent bond from these 4 electrons that are in the valence will kind of share that shell with another atom. And that's why it forms this regular crystalline structure. So you've got these 4 bonds in all these different directions. When we dope it, we will see how that changes. So if we add material if they add free electrons, then it gives that crystal a negative charge or an excess of free electrons. We call it N-type semiconductor material. And they call it majority charge carriers are electrons in the N-type. The charge carriers in the P-type are holes. Holes are not physical, they're just outer shells that are missing an electron, but they can accept an electron. And when you fill the hole, another hole pops up somewhere else. So they have an apparent movement in the opposite direction of the electrons. So which of the following semiconductor materials contains excess free electrons?
A.
Okay. So we talked about EMP and extra electrons, the holes. If we put in what we call an acceptor impurity, okay, we're going to add holes to that material and make it a p-type. So it will accept free electrons, which is called why they call it an acceptor. If we add an impurity that adds free electrons in the crystal, then it becomes a donor. So here is an N-type material where it's got I believe that's a phosphorus atom, which is one of the things they use. And that has 5 electrons in its outer shell versus the 4 in the silicon. So you've got one that doesn't have a pair to match up with. So it becomes basically a free electron and gives that crystal a negative charge. In the p-type material, one of the common ones is boron, which is only 3. So we wind up with another mismatched pair. In this case, we've got a hole. So that becomes an acceptor. So what's the name given to an impurity atom that adds holes to a semiconductor crystal structure?
Acceptor.
Yep.
C.
Exception. Okay, so like I mentioned earlier, for high frequency like microwave, instead of silicon, we use gallium arsenide or gallium nitride. Gallium arsenide is probably more popular. It has a higher electron mobility than silicon, which is one of the reasons why it's used. So that allows the efficiency conduction to be faster. In what application is gallium arsenide used as a semiconductor material?
Microwave circuits.
Microwave, very high frequencies. Okay, when we take 2 of these materials and put them together, it creates what we call a p-n junction. So we have electrons in the N-type material, and we have holes in the p-type material. And under steady state conditions, those electrons will tend to migrate to fill in the holes in the p-type. And that interface between them, it creates what's called a depletion region, where the holes are all filled with electrons. As we apply an electric field or electric force across the region, okay, you're going to generate, or you're going to supply electrons into the N material, or the P material, not N material, and supplying holes in the other, and you're going to change that depletion region. and you get a voltage across it, which is part of that threshold voltage we talked about, part of the energy gap. So the most important thing they discovered with the p-n junction is that it will only conduct current flow, conventional current flow, or electron flow in the opposite direction when it's what we call forward bias. When there's a positive voltage on the P material relative to a voltage on the N material. And for silicon, that turns out to be around 0.7 volts. For germanium, it's about 0.3 volts. Probably getting ahead there, it's probably on the next chart. When you reverse bias that diode, it will not conduct current because you're basically separating the holes in the electrons in the depletion region. This is what this part down here is trying to explain. So you widen the depletion region. Now the other effect, which will come up a little later on some of the diodes, is that depletion region acts like a dielectric. And you have, on one side of the depletion region, you have electrons, and the other side you have holes. So you get positive and negative separated by a dielectric with an electric field. So remember what that's called. It's called a capacitor. So when we talk about a varactor, that's how it works, by reverse bias and changing the width of the depletion region, which varies the capacitance. So it becomes a voltage controlled capacitor. It turns out all p-n junctions have capacitance due to that depletion region, which is one of the things that you have to take into account in circuit design, is that intrinsic capacitance. And so when you look at the structure for a p-n junction, and you can see the junction here, and this becomes the depletion region, which is shown better over here. And you get this electric field across it, which is the potential that you have to offset when you bias the junction. It will not conduct until you get up to that threshold voltage. And then it will conduct electrons from the union P. So why does a p-n junction diode not conduct current when reverse bias?
Because the depletion region is wide.
Right.
B? Yep.
Sorry. Was there a question?
No.
So if we take a third piece of material, we can make a transistor. I think they accidentally discovered this. They invented transistors. So if we have a p-n junction, which is our diode, and we add another piece of N material, then it becomes an NPN sandwich. And you actually have, in essence, two diodes back to back. But because of the physics in there, the current through the p-n junction of the base to the emitter will allow current to flow from the collector to the emitter, the N through the P to the N. And I'm not going to go into the physics of how that actually works, because I don't understand it. I'm not even sure I did in college.
But that's why you use transistors for like switching from
Well, that's one of the reasons. You either use transistors to switch or
for an
amplifier.
amplifier, right?
The direction.
Say that.
The direction.
What do you mean?
whether
going
you're,
between the emitter and
which
collector.
way the energy's
Which way the
flowing.
energy's flowing, really.
It's some kind of like a multiplier effect when you have current flowing from to the PN junction, base emitter. It somehow avalanches current from the collector to emitter, and I don't understand the physics of that part.
To whether you're providing something to enhance the depletion region or,
Right, but that's true just in the diode part,
Right.
the PN junction.
right.
How the collector emitter stuff works, I just believe them. But I don't actually know how that works. But basically, that's how you make a standard bipolar transistor. And if you reverse it and you do a PNP, okay, it's kind of the reciprocal. You use opposite voltages. This is the symbol that you'll see on a schematic for an NPN, where the diode, little triangle down there between the base and emitter, is going, from the base, which is P material, to the emitter, which is N material. In the NPN, it's just the opposite. It's P and P junction. That I see.
Did you learn like pointing in permanently or not?
Yeah, something like that.
Not pointing in.
All I really remember is that the arrow goes out, it's an NPN, therefore it goes the other way. It's the opposite.
Not pointing in. Not in.
Right. Okay, so this one kind of shows more of how that magic works. And we've got a voltage bias down here. If I can find the balance again.
Go to the right. Right. It's at the bottom of the screen, go up.
You can see it?
Yep.
I can't.
Can you go up?
I'm going up.
Oh, maybe there's something else.
So anyway. So what we're showing here is the bias on the base emitter junction. And you're seeing that white arrow, okay, of the current flow. And they're showing some recombination between the white and the gray arrow. And you're seeing electrons going from emitter to collector as a result of that base current going from base to emitter. Now, how that really works, I don't know. But anyway, this is where we get the 0.6, 0.7 volts, which you need to bias the base to emitter to cause current to flow. And the more current, after you reach that voltage threshold, the more collector emitter current. Yeah, so it's proportional. And it's a function of the gain, which is called HFE. So there's a multiplier ratio of the collector emitter current to the base emitter current. And for a typical little transistor, it may be 50 to 100. So for every microamp on base to emitter, you get 50 to 100 microamps collector to emitter. So that's where the gain comes from. Which of the following indicates a silicon NPN junction transistor is biased on?
Delta T.
0.6 to 0.7 volts. And it'll vary by transistor. And maybe even within the particular, like a 2N2222, if you actually measure them, they're probably slightly different for each one. So with the NPN transistor, when we forward bias the base, get a small base current, much larger collector current, which is the term we call HFE, or the collector to base current ratio. A lot of your relatively cheap multimeters will even have a 3-pin socket on them. You can measure the HFE for a transistor. So what is the beta, which is also called HFE, of a bipolar junction transistor?
B.
It bounces back. Change the collector current with respect to base, or the ratio of collector to base current. And a lot of times they'll refer to that as beta. There's also an alpha, which will be coming up. Although I was not able to find a single data sheet for a transistor that listed alpha.
Hmm.
And here's alpha. And it's defined as the frequency at which a grounded based amplifier, this circuit, has a current gain of 0.7 or 0.707, this is 3 dB down, of the gain attainable at 1 kilohertz. So I tried to simulate that, and the gain down here at kilohertz, basically this is flat until you get up to this point. And this line right there is approximately where that's 0.707 of this gain. And it's, I don't know. What frequency is that?
5 megahertz,
Okay.
just a little above 5 megahertz.
Now, I don't know how realistic that is, but I did it with a simulator in their version of a QN3904, which is a relatively popular general purpose transistor. But essentially, alpha is the frequency at which the F, or the collector current divided by the emitter current is 0.707. And that definition I could find, but nobody listed alpha cutoff, what they call it, for any of the transistor data sheets I looked at. So I kind of wonder why they even put it in here. Must be important for some reason. Because it is a question. What term indicates the frequency at which the grounded base current gain of a transistor has decreased to 0.7 of the gain obtainable at 1 kilohertz?
D.
Cutoff. Alpha cutoff. So it stops, basically stops having gain. You know, you're losing gain. Okay, now we have field effect transistors. Like I said, they work more like a vacuum, where bipolars are current devices, field effect transistors are voltage devices. And like a bipolar transistor, it's got 3 elements. In this case, we call them gate, drain, and source. I don't know that I mentioned on the other one. Bipolar has base, emitter, and collector. They do equivalent functions. The figures over here on the right, and this is actually one on the exam. So we're showing this number 1 is a P channel. You notice where the arrow is going. And field effect transistor. If you look at number 2, you see that the gate symbol doesn't make contact with the drain source. It actually shows it in parallel. And that's because that creates a electric field between the gate and the drain and the source substrate. And that electric field is what controls the current flow from drain to source. And it has two versions also, a P and an N. There's also dual gate down here at 4 and 5. Don't know much about those. And the last one down there is what, an N-channel FET. And just like bipolars, they're made out of the same P and N type semiconductor material. So in figure 6.1, what is the symbol for an N-channel dual gate MOSFET? For
So the N channel, I try to remember the arrow gets pulled by the gate.
what's the schematic for a P-channel junction FET?
Number one.
I thought I drew circles on my chart. It didn't show up. Okay, MOSFETs. They have a very high impedance, particularly compared to bipolar transistors. Because of that, they use them in a lot of test equipment where you want to minimize the load you're putting on the circuit for testing. The downside is they're very sensitive to electrostatic discharge. So in some cases, they actually, on the substrate, put Zener diodes across the gates to conduct any high voltages static that gets into the gate. Otherwise, it will zap. Those are the kind that you all, and if they don't have the Zeners, they always have warnings on them, and they're in conductive bags or conductive foam to keep them shorted out so that you don't get static. You're supposed to be very careful when you handle them.
Yeah, a little
You're
wrist.
supposed to be have a wrist strap to ground, so when the lightning comes, you're good.
Yeah, you'll sacrifice yourself.
See that one across the carpet like this, but you hold it.
Your arm anyway.
This shows one of the devices and where they put the Zener diodes is over volt protection. You notice they're back to back because the Zener will conduct forward, but it only conducts in reverse at the Zener voltage. So that way, this will act as a short circuit whenever you exceed the Zener voltage, positive or negative. And most of the devices, whether they have it on the gates or not, will have a Zener across the drain to source.
So it's saying the static is gonna exceed the.
Well, static can be thousands.
Right, but that's why it's reversed,
What?
because it'll conduct
Yeah, Zener conducts in the forward
with static.
at the normal threshold. In fact, the Zener diodes are made so it's probably less than 0.6 volts forward.
Yeah.
But the reverse voltage is going to be the Zener effect, and that's, I don't know how they control it, but they can control the breakdown voltage, which is the reverse voltage. So you can get a 5-volt Zener or a 12-volt Zener, or all kinds of different voltage values. It makes a very simple DC power supply, regular, just resistor and a Zener and a capacitor. As long as you're not drawing a lot of current. How does DC input impedance at the gate of a field effect transistor compare with the DC input impedance of a bipolar transistor? So comparing field effect to bipolar.
has a higher input.
Right. There's no current flow on the gate to the source, just a voltage. Why do many MOSFET devices have internally connected Zener diodes on the gates?
Delta.
Okay, enhancement mode and depletion mode. Most of the FETs tend to be enhancement mode devices, which means you have to apply a voltage to the gate to get current to flow. There are some called depletion mode, where with no voltage on the gate, current will flow. So you actually have to apply a negative voltage on the gate of the depletion mode to control the current flow. Whereas you apply a positive signal and bias on the enhancement mode FET to cause it to conduct. And this is supposed to explain the difference. But I don't have the text to go with it, but essentially the difference appears to be that they put additional P material in between, which makes this a depletion mode. I don't understand any more about it than that. But they're physically slightly different. And they definitely work different, because I ran into it before I learned about depletion mode, wondered why, when I was biasing it, nothing was happening. So what is a depletion mode FET? Okay. Allows current to flow when there's no voltage on the gate. Okay.
I gotta walk out. The big donut. What's the takeaway?
I'll see you
The
next
big
Saturday.
donut.
All right. Let's see.
Go ahead, Jimmy, did you read it?
Oh, Rick. I'll try to get them on YouTube the next day or two. Uh,
He goes through this every time.
yeah, I know. I don't have my mouse over here. Oh, there we go. Well, I saw it for an instant. There we go.